Hi, I'm Alistair, I'm a games designer, and in this video I'd like to show you an escape room puzzle which I call the heart transplant. Now, to demonstrate this puzzle I'm going to need an assistant, so meet Bob. Now, in life Bob was pretty heartless, and in death he remains heartless still, not just because he's missing his vital organs, but because as he died and rigor mortis set in, his final callous act was to grab securely hold of this key which players need if they're going to progress in the room. If only Bob had a heart, maybe he would let players have that key. Now fortunately, there is a heart here as well, but if players tried to just, insert it into Bob's skeleton, it's not going to do anything because at the moment it's not beating. So to solve that problem, they need to find a battery such as this one. Now, I'm not a cardiac surgeon, but I would imagine that if I connect the black terminal of a battery to the black wiggly bit that comes out of a heart, which I'll assume is a vein, and if I take the red terminal of a battery and connect it to the red wiggly bit of a heart, which I'll assume is an artery, you can see that the heart starts pulsing. So now that the heart has a heartbeat, we can try to give it to Bob. And if I put it near his head, you'll see nothing happens. If I put it near his pelvis, nothing happens. What we need to do is actually to insert it into his ribcage. And when we do that, you'll see that Bob is filled with the lifeblood of human kindness, and he releases his grip, or at least the maglock releases, and players can retrieve the key and carry on with the room. Now, just to be clear here, if I just put that for a second, if the players remove the battery from the heart and it stops pulsing, Bob grabs hold of the key again. Likewise, if I power the heart up but actually take it out of his skeleton, Bob's not going to give us the key either. The key, the heart rather, does need to be pulsing through its connection with the battery, and it needs to be inserted approximately into his ribcage. So now let me give you a brief overview of how this puzzle works and the technology it uses. So starting with the battery pack, this really is just a battery pack. Inside here there's a USB power bank, and it has a 5-volt and a ground output going to these terminals at the top. I just put it inside this box because I thought it made it look more thematically interesting to have to clip crocodile clips to it. Now the heart, this is a 3D printed heart, and inside here there's an Arduino. The Arduino is powered by the 5-volt and ground lines that are coming from the battery, and when it powers up it's running a sketch that is causing some Neopixel LEDs to flash this pulsating pattern to make it look like the heart's beating. But there's another component inside here as well. And that component is one of these. This is an RF transmitter. It operates at 433 megahertz, and it is a very cheap, very common component that you'll see used in a lot of Arduino projects when people want to try to transmit data remotely to other devices, to control drones, or to send data between Arduinos, for example. And if you look up forums of users who are trying to use components like this, you'll find a lot of people complain about the relatively short distance that they actually work between. So people were trying to transmit data, hundreds of meters between devices and things like that, and they say, well, these are no good because they could only reliably get data to be sent, 40 or 50 centimeters sometimes. And that's really what gave me the idea for this puzzle, because I thought, well, hang on a minute, if these devices can only work over 40 or 50 centimeters, that would make them ideal for kind of proximity detection of props in an escape room. There's lots of escape room puzzles that require players to place items in a particular position. So normally we use magnets for that, or we use RFID sensors. But they are quite precise, and the objects need to be placed in exactly the right spot. If you're working with kind of large-scale props like this, I didn't want players to have to kind of slot the heart into an exact location for it to line up with the sensor. I just wanted it to be somewhere in the rib cage area, And these sensors actually worked really well. Well, they're not sensors at all. So what happens is every time the heart beats like this, in addition to making those LEDs pulse, it sends out a packet of data from a transmitter unit here. Inside Bob's ribcage, there is a receiver unit. So this is a corresponding 433 megahertz receiver unit. And so long as the heart is roughly in this kind of area, that packet of data will be received by an Arduino that's here. Obviously in a real life escape room you'd want that Arduino mounted under the board, but I've just got it on the top so you can see it's here. This controls a relay here, which in turn controls power to the maglock at the end, and it's the maglock that it is securing the key here. Now, before I show you the code that's actually running the puzzle, I wanted to take a little bit of time to explain the steps that I took to get there. Because obviously I'm not really using these modules for the purposes they were intended for. These are designed for RF communication. They're not designed as proximity sensors. So to get them to work like that, I needed to do a little bit of experimentation. So what I've got here in front of me is, on this side of the board, I've got an Arduino Nano that is connected to the RF transmitter module. That's this squarer one. And you can see it's got 3 connections to the Arduino. It's got ground, 5 volt, and a single data line, which I've got connected to pin 13. And on this side here, this is the receiver unit, which is the longer rectangular one. And again, this has 3 data lines. So we've got ground, 5 volt, and the receive line, which I've got going to pin A4. But I mean, that can be any pin at all. And in its absolute simplest state like this, what you can imagine this is kind of like a direct connection between these 2 Arduinos, but wirelessly. Any value I write to this pin here that goes to the transmit line, so if I write a high or a low value, I can then read that same value from the receive pin on this side. So to demonstrate that, I'm going to load the simplest possible example. I'm going to load the blink sketch onto this Arduino here. The blink sketch comes with the Arduino IDE, and all it does is it's going to send a high value for a second and then a low value for a second, and it's just going to keep on iterating through that loop. It's also going to make this LED flash at the same time, so you can see when it's sending a 1 or a 0. And then on this side, I'm going to load a very simple receive sketch, and all this is going to do is read the value from this A4 pin and output it to the serial connection. And there you can see the output from the serial plotter. These are the values that are being read by this Arduino here attached to the receiver, that are being transmitted from this Arduino here that's running the blink sketch. And you can see that regular pattern of 1s and 0s that correspond to the high and low values being written to the pin here. And in fact, you'll also notice that that pattern kind of resembles a bit like an ECG pattern from a heart monitor anyway. So I kind of saw that and I thought, wow, this is fantastic. This could be the basis of what I need to measure whether my heart is in range or not. So I'd have the transmitter unit contained within my heart. I'd have the receiver unit here contained within the skeleton rib cage. And when the rib cage was able to detect this this heartbeat pattern, that's when it would know the heart was in range. However, there are still a few issues here. The problem is that we're looking at a digital signal of 1s and 0s. We've still really got no indication of signal strength or an amount of interference in that signal. You'll see that there are actually a few sort of glitches there. And if I were to put my hand in the way, or if I take the transmitter further away, for example, I'll try and carry it all the way over here, you'll see that we kind of get more noise in the signal, but it's not that it kind of just disappears. All that happens is you end up with a kind of an arbitrary pattern of ones and zeros. I appreciate you couldn't really see that on the camera, but that was me carrying that to about a metre off screen. And if I actually detach the transmitter completely, so now what we're doing is we're still trying to read values on the receiver, but no pulses being emitted. What you'll see is we now kind of get like just a random pattern of noise being detected. And what's happening here is the receiver is just picking up background radio signals. So it's not getting a regular pulse anymore, but it's not just getting a simple zero value either. And what I wanted to do was have some way of detecting whether this pulse was in range and I was getting a nice regular pulse, which it should now stabilise to show, there we go, or whether it was out of range. But that was kind of tricky to work out how to do. And that's why I decided not to just transmit ones and zeros, but to actually transmit a recognised packet of data, a message as it were, and I would then detect whether that message had been received correctly by the receiver as an indication of the level of noise that was present. Basically, the more packets of data that got corrupt or not received, that would give me an indication of how far away the receiver and the transmitter were. So now I tested how the core functionality of the puzzle was going to work using that RF transmitter and receiver module. I could add the other components as well. So starting with the heart. So I downloaded a 3D model of a heart. It seems pretty anatomically correct. It's about the right size and it's hollow and it prints in 2 halves. And what that means is that there's actually plenty of room inside for me to fit all the components I wanted. So you can see I passed through the red and the black cable from the outside through this whatever aortic thing is. And the first thing they go into, you'll be able to see there hopefully, is a little chock block there. So that serves 2 purposes, one of which is it reduces the wire diameter. So I've got this nice thick chunky wire going in, I think this is AWG10. And this block here reduces that to a much smaller cable size for the internal wiring. And secondly, it acts as a kind of a strain relief. It prevents the cable being pulled out through that hole there because it physically won't fit. Then the Arduino itself and the RF transmitter, they're located inside this tube in the middle. If I show you down the end, hopefully you'll be able to see that they're in there. So I've got the RF transmitter soldered to a protoboard. I've also got the Arduino Nano in there. And then wrapped around the outside, I've got a strip of Neopixel lights, and then all of that bundle is taped together with this masking tape. And that's got 2 purposes. The first one is literally to just package everything together in a neat bundle so that I can close it up inside the heart. And the second purpose is to act as a diffuser for the LED lights. So when they light up and do that pulsating pattern, I want that light to diffuse over the entire surface of the heart. I don't want it to seem like kind of harsh points. So that's why I've wrapped the whole thing in kind of this semi-opaque masking tape like that. And then in terms of the electronics on Bob's side, so Bob, as we know, well, he has the receiver unit, which I just showed you there. That's wired to an Arduino, and the Arduino is wired to a 5-volt relay module. And then on the load side of the relay, I've got a 12-volt DC power supply, and I've got a maglock, and I've also got a 12-volt LED ring. And the way this is connected here, so I've got the 12-volt power supply going to the common terminal of the relay. I've got the maglock powered through the normally closed side of the relay, and I've got the LED ring on the normally open side. So what happens when the puzzle is in its default state and Bob is clinging securely onto the key, the maglock is energized because that's on the normally closed side of the relay. When players find the heart, power it up through the battery, insert it into the ribcage, that signal is detected and the Arduino sends a trigger to switch the relay over to the other side. That cuts power to the maglock, but in doing so it diverts it to the LED ring instead, which is placed around Bob's hand where the key is. Now, I've mentioned this in a few videos in the past, the importance of letting players know when there's been a change of state of something in an escape room. If you've put an input into a puzzle and it's done something, if a door has popped open or if something else has changed, you need to draw players' attention to it. And that's what the light here is doing. And it comes free really from the fact that I'm using a relay to deactivate the maglock anyway. That switches over to the normally open side, and it's like, well, I may as well use that 12 volt power to supply energy to this LED light instead. And when players de-energise the maglock, they'll have their attention drawn to the fact that the key is now released and they can take it and carry on in the room. And here's a wiring diagram of those components laid out in fritzing. So over this side we've got Bob and the components related to him. And on this side we've got Bob's heart and the components related to that. And I just want to pick out a few details here. So we'll start with Bob's side. And if we just zoom in, so we've got our RF receiver module connected to our Arduino. And this has got 4 pins. It's got VCC, which is connected to 5 volts. It's got ground, which is connected to ground, and then for some reason the middle 2 pins on these modules are both data outlines. I have no idea why they designed it like that, but it doesn't matter which one you use. So you can just take the data from one of those lines here and connect it to digital pin 8 on the Arduino. And then on this side we've got the relay. So this is a 5 volt relay module, so again it's connected to 5 volts and ground. And we also have the signal line, which is how the Arduino is going to control the relay output. That's connected to pin A0. Then on the load side of the relay, as I mentioned, we've got a 12 volt DC input, and the positive terminal of that is connected to the common pin of the relay in the middle. And then on the normally closed side, we have the positive wire from the maglock. On the normally open side, we have the positive wire to the LED ring. I'm representing that just as a single LED here, but it's my LED ring. And then the negative sides, the cathodes of both of those, are connected to the negative side of the DC barrel input. As I explained, what that means is when the Arduino sends a signal through this A0 pin, so when it writes a low value to there, the relay on this side is going to switch across from the normally closed to the normally open side, and that's going to divert this DC input here between the maglock and the LED ring. Okay, so if we then take a look at Bob's heart and what's going on over here. So here we've got our Arduino again, and we've got it connected to the transmitter unit. Now this time we've only got 3 pins. So we've got data, which we're connecting to digital pin 9 for the transmit. We've got ground, which is connected to ground, and then we've got VCC, which is connected to 5 volts. But notice that I've put a resistor in the line here. Now, at the moment this is just a 100 ohm resistor, but this needs a little bit of explanation. So remember, what we're doing here is we are trying to create effectively a crude proximity detection from when the transmitter gets within range of the receiver. We're going to activate the relay on this side. So we want to be able to in some way control the distance through which this signal is received. And there's a couple of different ways you can do that. We've already taken one measure by not installing the external aerials into the transmitter and receiver. That's going to reduce the signal distance somewhat. But you might want to kind of fine-tune it a bit more. In the example video I showed you, I wanted the relay to be activated when the transmitter was in about 30 or 40 centimeters range, because that was the size of Bob's ribcage, and I wanted the puzzle to be activated when the heart was somewhere in that area. So how do you go about fine-tuning the reception range to trigger the maglock when the transmitter is at that kind of distance? Well, that's what this resistor is going to help do, because placing a resistor on the VCC line here is going to limit the power of the transmitter, and that's going to reduce the range of the signal that's broadcast. Now, I should point out that this is actually only one of the various factors that you can adjust in order to fine-tune this kind of distance here. This is a hardware measure, and I would probably recommend you actually start off with this resistor not in place at all. Do a direct connection from VCC through to 5 volts initially, because there are also some changes you can make on the software side of things as well that are going to affect this detection range. But I've just included it here in the wiring diagram to show that that is one of the factors you can vary, and you might want to vary that when you get this puzzle set up in your particular setting and you decide how kind of sensitive you want that reception to be. So that's why I've included it there. And then on this side here we've got our strip of WS2812B or Neopixel LEDs. They are connected once again to 5 volt and to ground, and we have the data input line here which is connected to digital pin 2 through a 330 ohm resistor. Now this time you do want that resistor to be there. That's not actually going to limit the brightness of the LEDs at all. That's not what it's for. It's not a series current limiting resistor like you have in a regular LED. That's actually to protect the circuitry here. So somewhere, it doesn't need to be an exact value, but somewhere between 300 and 500 ohms is recommended, just between the Arduino and the first LED in the strip before the first data input there. And notice I've also got a capacitor between the ground and the 5 volt lines, just again close to the first LED in the strip. And that's because when the LEDs come on, when they start pulsating, they're going to draw quite a lot of current, and we just want to have that little reserve sort of power supply close to them there that's going to help smooth out that sudden current draw when the LEDs all come on. So again, that's always best practice when you use a strip of LEDs like this. Place a capacitor close to the first one. So this is rated for 6.3 volts, and I think it's 1 millifarads, and that's it. So this is the code for the transmitter side of the puzzle. So this is running on the Arduino that is inside the heart. And it starts at the top. You'll see I'm using 2 external libraries. So I'm using the fast LED library to control the programmable LEDs, and that's what's going to make them light up in that pulsating pattern to look like a heart. I've used the fast LED library in lots of projects. You can download it here. And then for the radio transmitter itself, I'm going to use the radio head library, which you can grab from here. Now, I showed in the video that if you just want to write high or low values to the transmitter, that's really simple to do. But what I'm going to do here is actually send a structured message instead. And I want it to have kind of error correction and all those kind of things. And the radio head library is great for that. It supports lots of different sorts of radio receiver and transmitter modules as well. So that is definitely worth checking out. And then we go on to the constants, which are variables that do not change over the duration of the code. Now, the value I want to draw your attention to is this speed variable at the top here. So what this is the speed at which data is going to be broadcast by the transmitter. And we've got a value here of 4,000. So that means 4,000 bits per second. So what we're going to do is we're going to specify a message that's going to get broadcast. That message will be converted into bits of ones and zeros. And then the transmitter is going to broadcast those bits at a rate of 4,000 per second. And that's important for 2 reasons, really. The first one is that the receiver needs to be operating at the same bit rate as the transmitter. Otherwise, it's not going to be able to successfully read the message at the other end. So we need to make sure that this 4,000 value is copied into our receiver code as well. And the second reason it's important is because remember that we're doing this as a way of approximating the distance from the transmitter to the receiver. And generally speaking, there's an inverse relationship between the speed of data transmission of a radio signal and the distance it can be transmitted over. If you want to transmit at a very fast rate, if you want to transmit a lot of data over a radio signal, generally you can only do so over a small distance. And likewise, if you want to transmit over a very, very long distance, you generally do so at low bit rates. And one simple way of thinking about that is that when you are transmitting at a fast speed, there is less time that the transmitter sort of stays in each of the high and low states, and as a result it's more susceptible to any short bursts of high frequency noise. If there's some other source of radio interference nearby, if you're only spending a very short amount of time on each of the logic values, that could completely obliterate the signal and that entire packet of data will be lost. So this is a very, very crude way. You're not going to find a nice formula that's going to convert between speed and distance here, but it is one of the ways that you can kind of configure this particular setup to work over different distances. Now I've put some values here in the comments. I found that if I raised this to 8,000, I was only reliably detecting packets of data at a distance of about 5 centimeters between transmitter and receiver. If I lowered it to 1,000 bits per second instead, I was getting somewhere around 10 meters. So the value that worked for me, given all the other settings which I'm going to show you in a minute as well, was about 4,000. But this is one of the variables to be aware of that you can configure and alter how this puzzle works in terms of a proximity detector. Okay, the other constants are thankfully a bit easier to explain. So we've got the pin that is connected to the transmitter. Now we're looking at the transmitter code here, so we're not actually using a receive pin. We don't have a receiver connected in the heart, but the Radiohead library still requires you to specify a pin. So I'm just using 8, which will be the pin that I actually use on the receiver side anyway. We've also got the total number of LEDs that we're going to light up with fast LED, and we've got the heart rate, which is going to determine how frequently the LEDs are made to flash that pulsating pattern. Okay, so then we go on to the globals. So globals are variables which are going to be shared between different functions in the code. We initialize the Radiohead driver at the specified speed and with the receive and transmit pins we just listed above. We create an array of LEDs to represent the colours that we want each of the LEDs to light up. We have a variable that's going to keep track of the last time that a message was sent by the heart. We're sending one message each time the heart beats, so this is also the last time that we lit the LEDs or beated the heart. It's all the same thing. We define a character array that is going to be the message that is broadcast by that transmitter each time the heart beats. Now this is another variable here that can affect the functionality of this code. So it's a character array, and I'm defining a character array that's 32 bytes long, because I wanted it to be long enough to make sure that it contains the whole message that I want to send. So you can actually write a short text message in that space. Now, as it happens, I'm actually only going to be sending a number in that space instead. I'm just going to be sending the message number. But the longer the message that you send and broadcast, the more bits of data it's going to contain. And that means that there's more chance that somewhere during broadcast of that message it will become corrupt and it won't be correctly received at the other end. So this is another value that potentially can affect the behavior of your code, just to be aware of there. So we're also going to keep track of the number of messages that have been sent. So this is a simple index number here. Again, I'm storing that as an unsigned long, so this can be a quite large number of messages before that rolls over. And we go to the setup. So setup runs when the code first starts up, when the heart first receives power. I'm defining the serial connection here, although I'm only using that for debugging purposes. That's not actually going to be used anywhere in the live code. We initialize our LEDs with the fast LED library, and we also initialize the radio transmitter by calling the init method on the radio head driver. And then we go into the loop function. So the loop function runs round and around for as long as the heart receives power, so as long as it's plugged into that battery. And the first thing we do is we grab the current timestamp. So millis is a function that tells you how many milliseconds the code has been running for, and we'll store that in a variable called now. And then what we'll do is we will compare that value to the last time that we sent a message. So I'm sending one message from the transmitter every time the heart beats. So last sent time, you can also think of heart rate time, or it's also the same time that the LEDs pulse. It's all synchronized to the same thing. So we'll compare how long it's been, how much time has elapsed between now and the last time we beat. If that's greater than the heart rate, which we defined at the top, so if it's been more than 1.4 seconds since the last time we beat the heart, well, it's time to beat again. Well, what do we do? First of all, I'm going to use the snprintf command. So this is going to copy an integer value here, which is message number. So the number of messages we've sent, I'm going to copy that into the message to send character array. It is an unsigned long, which is what the format there means, and it's 32 bits of data. So if you're not familiar with C terminology, so this is a standard C function. Essentially all it's doing is it's converting a long integer value here into a character array here. It's a slightly peculiar way of laying it out if you're not familiar with it, but that's what it's doing. It's saying take this integer, convert it to a character array, because that's the format we're going to use to send it over our transmitter. I just send some serial data out so that when it is plugged into my PC I can see what's going on. And then we call the driver.send method from the Radiohead library to actually send that character array. We tell it how many how long the message is that's going to send, how many bits of data there are that need to be encoded, and then we wait for that packet to be sent. And then once that's all done, we update our last sent time so that next time we come through this loop we'll be able to tell whether 1.4 seconds has elapsed again. And we also increment the counter to keep track of how many times our heart has beat. The next section of code, this is all about making the LEDs light up. So I tried a number of different approaches here to try to make something that looked like a heart pulsing. There's no real right way of doing it because hearts obviously don't actually glow, but this is something that kind of just felt right to me. So I'm actually defining two waves and overlaying them one on top of each other, because most people, when you think of a heart beating, you kind of get ba-dum, 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 ba-dum. So this one is going to be the B, and this one is going to be the dum. And that is why they are offset slightly. This one is 0.2 of a second behind this one, but other than that, they are both using the same functions. So it's going ba-dum, 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 and I'm adding them together with the QAdd8 library. So these are functions from the Fast LED library. The Fast LED library's got lots of useful functions for animating LEDs in different kind of patterns, in sine curves and different beats per minute and things like that. So this is just a function from that. So I'm adding together one wave that's going to give me a regular sort of primary beat, if you want, and then I'm adding to it a secondary rate to get the ba-dum at the end. That's going to give me a value called Y, and then what I'm doing is I'm looping over all the LEDs in the array, and I'm simply setting the red, green and blue values to just be that same value. So my LEDs are actually flashing up white. They're just looking red because they've been diffused through the red plastic of my heart. You know, that's all that's going on there. And then this function here, this actually sets the values in the LEDs array. This then actually updates them and sends them out to the LED strip. And then just at the end, this is actually my definition of the triangle wave function. So what this does is it has a length of wave, it has the milliseconds that are elapsed, which I'm basing on millis or millis plus 200 to get that delay for the second wave, and how long I want the pulse to be. And you can see if we are if it's the first half of the beat, so if it's up to the midpoint of the wave, this simply increases, so it's like a triangle up to the full intensity. Once we're the other side, so once we're past the halfway point of the wave, it reduces again down to 0. That's why it's called a triangle wave, because it simply goes up and down and up and down, whereas a sine curve would give me a smooth curve like this. But I don't think that's really how most people think of a heart glowing. I think you think of more of it like that. But you know, this is just something you can play around with. That's purely for aesthetics. And this is the receiver code. So this is what's running on the Arduino that is inside or near Bob's ribcage. So again, we're including the Radiohead library. We go to the constants, and as I mentioned, we set the same speed, the same bits per second as the transmitter is broadcasting the message on. So we need to make sure those match. We'll also define the pins that we're using. So again, this time we're only using the receive pin, but we're still going to define a transmit pin, even though we're not going to use it, just because that's what the Radiohead library expects in the constructor. And we also define the pin that our relay is going to be plugged into, and this is what's going to release the key from the maglock when the heart is in range. So we once again, as with the transmitter sketch, we construct an instance of the Radiohead driver at the speed and the receive and transmit pin specified. We also keep track of the time that the last message was received. So this time we're not keeping track of when it was last broadcast, we're keeping track of when a message was received. And again, we keep track of the messages received rather than the messages sent. And then we go on to the setup function. So again, serial connection for debugging. We'll initialize the relay pin. I'm using an active low relay, so I'm going to send an initial signal to it of high, and when the heart transmission is received, we're going to set that to low. I'm also just going to use the built-in LED pin. This is normally attached to pin 13 on an Arduino, just for a little bit of visual output as to the state of the controller as well. And we'll initialize the RF receiver just as before. So a lot of that is very, very similar to I just showed you in the transmitter code. The difference now comes in the behavior we want when a signal is received. So in the loop function, what we do is we create a character array that's going to store any incoming messages. So just as the transmitter code created a character array and populated it with a message before it broadcast it, here we're going to create a character array and we're going to populate it when we receive a message. We'll keep track of the current timestamp, and what I'm going to do here is I'm just going to say if it's been more than a second since we last detected a heartbeat, then I'm going to turn the LED off, and I'm going to also keep the maglock energized. So this is the same as the initial state that we defined at the top here. Now you'll recall that in the transmit code, I'm actually setting the heartbeat there as every 1400 milliseconds. So because I've got 1000 here, what this is going to do is, assuming that we actually detect every signal that's sent by the heart, we detect every single beat, this will leave a 0.4 millisecond gap when before the next heartbeat is received, when the relay is going to become locked again. And that's why when you saw the video at the beginning of the code, you'll see that there was kind of a clicking and a light flashing on and off. And what players actually have to do is they have to time their grabbing of the key to coincide with the pulse rate, so that they can only grab it at a time when the relay is actually unlocked. If you set that to a higher value, so if we set it to anything higher than 1400, that is the frequency with which we expect to receive every single heartbeat. So if the heart's in range there, you're not going to get that on-off pattern. You'll actually have the maglock remain unlocked all the time for as long as the heart is in range. So that's up to you how you want that behaviour to work. I quite liked having it, the extra added thing of timing it with the pulse to grab the key, and I also like the fact that that made the light flash to indicate to players that there was something to do there. But you could set that to any value higher than 1400 if you wanted to, and it would just stay completely unlocked while the heart was in range. And now we go on to this section here. So this is what do we do when we do detect a heart signal. This bit here is activated if we haven't received a pulse for a while, and then this function here, so this is the receive function from our radio head driver, and we'll call it with the buffer that we defined at the top, which is actually going to store the contents of any message received. So while we're inside this bracket here, what we can do is, okay, we've detected, we've caught a signal, and it is decoded correctly. The error checking and everything has passed. Let's print out what it was. And so what we expect this to print is the message number, is the index number that was sent by the transmitter. And remember, the transmitter is keeping count of the number of messages it sent, and we are also keeping track of the number of messages we received. So that's something, if you wanted to, you could make use of. It's certainly very useful in debugging, but you can actually use it in the live puzzle as well, is to compare how many messages have been sent and how many messages have been received, and use that as a proxy for an indication of the signal strength as well. I've also put in these comments down below a couple of other ways that you might want to act on a message received. So because we're incrementing the count, maybe you want to only do something when a certain number of messages have been received. So I'll just put a value 3 there. You can set that to anything you want. Or because we're also keeping track of the time now and the time when the message was last received here, maybe we want to say, have we received so many messages within a certain space of time? That's another way you could potentially measure the quality of the signal between the transmitter and the receiver, is to say we know the rate they're being transmitted at, which is every 1.4 seconds. Let's see if we receive 10 in the space of 10 times that amount, for example. That would be a way of testing the quality of our radio signal. Or again, maybe you want to actually test the value of the message received. One of the advantages of using the Radiohead library is I'm no longer just sending an arbitrary 1 or 0 value. I'm actually sending a message which we can read and we can act upon. So it's a string, and maybe rather than just having a numeric value, we wanted to write a word. So if we'd have made the transmitter send the word pulse every time there was a pulse of the heart, we could write some code here to say, okay, we want to act differently when that message is received than when another message is received. So there's lots of different ways, and I do encourage you to try these out, because like I said, this is a puzzle that does change depending on your environmental conditions and the exact hardware and lots of things, and you might find that one of these approaches works better for you than another. But what I've actually got at the bottom here, this is kind of the simplest version as it is, which is to do no additional tests at all. All that we know, because we're still within this code bracket here, we know that a message has been successfully received from the heart, and based on that, what we're going to do is we're going to light up the LED, we're going to release the maglock, so we'll write a low value to the relay, and we'll keep track of the time that this message was received. What that means is that we come through again. If it's more than a second until we get the next heartbeat, that's when this section of code is activated here. So that just about brings me to the end of this video, and hopefully it's given you some ideas about how you can use these little RF modules in slightly unorthodox ways in an escape room. Now, it might be that there are radio engineers watching this who are horrified by what I'm proposing. And to be clear, these are not designed to be proximity sensors. I'm using them as a very, very crude way of measuring the distance between the transmitter and the receiver based on some kind of idea of the signal strength between those two modules. But I'm having to approximate what I mean by signal strength based on some arbitrary quantitative measure, like the number of packets of data lost or the rate at which messages are received. So there's a lot of assumptions and environmental factors all wrapped up in this approach. And to be fair, I should make it clear, you will probably have to tweak this to make it work in your particular setting. But throughout this video, I've tried to explain the approach I took and the way that I found values that worked for me, and there's no reason why you shouldn't be able to repeat those tests and find values that work for you in your environment as well. Now, as always, I will provide links to the exact components I'm using. I will put the code and the wiring diagram available to download from my Patreon account. I have all of the downloads available for all of my escape room projects are available over on Patreon. I'll put a link below. Please do check it out. And thank you all very much to my patrons who enable me to make these videos every month. I really appreciate each and every one of you. In the meantime, if you have any other questions or comments, please do let me know below. I'll do my best to answer them. And otherwise, on behalf of Bob and myself, I look forward to seeing you next time. All right, cheers, bye.